Chapter 12, Lesson 1, recap. We're looking at 12.1 for the fundamental counting principle and permutations. The important takeaways for this lesson is that counting things gives us a total. And why would we need a total? If I was asking for how many students out of a school, when we have that for maybe a probability, for information that we are given when we move forward for probability and statistics, we need to know totals. If we don't know the totals, like how many are in a school or how many choices that we have, if we don't know the total, then we can't do our probability because we always have some amount out of a total. And so what we are learning in 12.1 and 12.2 is how to find those total amounts. We are going to use this as we move forward. So it's very important that we know how to find the proper total at the beginning. So what we learned is that the fundamental counting principle tells us that we can take different events. So these are separate events, and that we can multiply the amount of choices we have from one event and each event afterwards, and it gives us the total ability, the total amount of combinations or lists or orders of things that we can have. So if we are going to talk about counting something, if we're going to talk about a permutation, permutations simply mean an ordering. So we are putting a bunch of things in order. If I have pencils and pens, for example, here, I can do, this is one order. When the order matters, I can rearrange them. There's a second order. Here's a third order. So we're simply putting things in order. Okay. Permutations are written with a capital P. That's our notation form. And then there's two numbers associated with it. The first number are the total items that you have. So in this case with the pens and the pencils, I have 3 different items. 1, 2, 3. 3 items. The items can either be the same type of item or they can be completely different types of items. And then I'm going to say how many of those items I want to choose. So if I have 3 pens and I'm choosing all 3 of them and putting them in an order, then I start with 3, taken 3 at a time. And we say this, taken at a time. So 3 writing utensils taken 3 at a time. Now, if I start with 3, but I only want to take 2 and then figure out how many orders that I have, which there's 2 different orders, I would say 3 things taken 2 at a time. If I have all 3 utensils and I only want to choose 1, how many options would I have? I would have a permutation of 3 things taken 1 at a time. And I would have 1, 2, or 3 options. So this is the notation that we use for permutation. Permutations always mean that the order matters. So it's telling us that if I have this set of writing utensils and I have mechanical, regular, and pen, that is a different counting order than if I had regular, mechanical, and pen. So when the order matters of first, second, and third, think of this as running a race. Comes in first, comes in second, comes in third. You could have the same 3 people place in your top 3, and yet the order would matter. One gets a gold. In one order, you get a gold, and in the other one, you might get a bronze. So the order matters here. All right. The formula for permutations comes from our fundamental counting method. And so I'm going to combine those together. Our fundamental counting says that when I have a certain number of items, say I'm taking 4 things and I start with 8 items that whenever I take them out of a group, these are removed items. So I start with 8 items. I'm going to take 1 out of the group. And so now I only have 7 items left. Then I would take the next item, out of the group. And so now for my next option, I can only pick from 6 items. Now, once I remove that item, for the next blank, the next choice, I only have 5 items. And you can see that this is going down, that every time we choose something, the pool from which we have to choose from goes down. So this is called a permutation without repetition. Okay. We could also say that it's without replacement, so we're not putting the items back in. And it creates a special kind of math notation called a factorial. A factorial is an exclamation at the end of a number. And it is a shortcut way. In this case, we would write 8 factorial. It is a shortcut way to say, start with this number and multiply by every number below it all the way until you get to 1. So whenever it's short, say 3 factorial, you might find it easier to write 3 times 2 times 1. But it's very inconvenient if you have 100 factorial to write 100 numbers all the way down to 1. So we have a shortcut form of that exclamation that tells us we're starting here and then we're going all the way down to 1. Now, when we take all of the items, and we get to go all the way down to 1. So I have 8 items. I'm going to use all 8 items. So I would have 8 blanks and go all the way down to 1. The easy notation is just to write 8 factorial. But our permutations help us with a formula that says, what if I start with 8 items, but I only want 3 of them? Somehow, whenever I write 8 factorial, when I use 8 factorial in my calculator with a factorial button, I need to only multiply 8 times 7 times 6. Now, initially, you can look at it and say, well, that's silly. Why even worry about the rest? Just go ahead and go 8 times 7 times 6. That's convenient when we only have 3, but what if I'm taking 11 things at a time and I have it multiplied by something that I've taken 13 things at a time? When we get to those bigger numbers, that's a lot of keystrokes versus our calculator has a factorial button that we can use, and so it eliminates all those keystrokes. So what we have here is we have a factorial, but I don't want the rest of this. I don't want 5, 4, 3, 2, and 1. So if we have this by multiplication, how do we get rid of something that is multiplied? We simply divide by the exact same thing, because something divided by itself is simply 1. So our 5s cancel, 4s cancels, 3 cancels, 2 cancels, and 1 cancels. And now we're left with what we really wanted in the first place. The way that we can write this is we could write 8 factorial divided by, what is our shorthand notation for what we wrote on the bottom? 5, 4, 3, 2, 1. 5 factorial. Another way to write this is 8 times 7 times 6 times 5 factorial. Because once I get to that number, I'm saying, and everything left until I get to 1 over 5 factorial. And we could say 5 factorial divided by 5 factorial cancels each other out. And we're simply left with the 3 that we wanted to in the first place. So a couple of different notations for that. These notations are important because our permutation formula says that for a permutation, so where order matters, of a certain number of items, so we call those n number of items taken r number at a time. Our formula says we're going to have n factorial, so our total number of items divided by, which means erasing the ones that we don't want, erasing n minus r factorial. Okay, so what would that look like in real life? If I have 8 items, like I said, taken 3 at a time, I would have 8 factorial over 8 minus 3 factorial. 8 minus 3 is 5. 8 factorial over 5 factorial. So that's what we got. So our 3 is how many we wanted. We wanted 8 items taken 3 at a time. That means we have 8 choices for the first one, 7 for the second, 6 for the third. And we don't want the rest all the way down to 1. We don't want the rest. So we divided by what we didn't want. And those canceled each other out and turned into the number 1. Okay. So when we take our N minus our R, it will always cancel out the extra blanks that we didn't want from our fundamental counting. All right. So fundamental counting is also important when we have separate events. So say we had separate events like choosing from shoes and shirts and ball caps and pants. When they are separate events, that one event has no bearing on the other event, we can use this and we can multiply together to get our options. How many options do we have? That's the fundamental counting part of it, and that's the part that stays with us as we work through on our permutations. So a couple of examples from homework says that if I have 2 events, so I have event 1 and I have event 2. In event 1, I can do it 1 way. In event 2, I can do it 3 ways. How many ways can I do it all together? When we have an and always means multiplication. So we're going to have 1 times 3 is going to say we've got 3 different ways that we can order our events. If we had, if we are, oops, sorry. If we have a license plate, we can work through, and they say we have 3 letters followed by 3 digits. So these here are letters. These here are digits. It says when they can be repeated, let's think about it. We have 26 options, then 26, then 26. Digits 0 to 9 is 10, 10, and 10. This is if we can repeat letters. If we can not repeat, that means whatever letter I chose first is out of the pool. So now I only have 25 letters to choose from. Then I only have 24 to choose from because we were removing something from our pool every single time. Same with the digits. It would be 10, 9, then 8. We could write this as a permutation of 26 letters taken 3 at a time and a permutation of 10 numbers taken 3 at a time. And that would give us the same numbers being multiplied as we work through there. For factorials, I would like for you to write those out, but you can just use your calculator factorial button to solve for those. Let's look at how to read a couple of permutations. We start with 3 items, so our pool has 3 items in it. We are taking them 3 at a time. That means I have 3 blanks. So how many ways can I put 3 items into 3 separate blanks? Well, for the first item, I have 3. He would go there. For the second blank, I now have 2 options. We move that guy over. For the third blank, I now just have 1 option. Right? What if we have 7 things taken 6 at a time? That means I'm starting with a pool of 7 items. I'm putting it into 6 separate blanks. How many different ways can I put these 7 items in 6 blanks? For the first blank, I have 7 options. Then I would have 6, 5, 4, 3, and 2. 3 and 2. To write that out, it tells us we take our total number, so 7 factorial, divided by these numbers subtracted, 7 minus 6 factorial, which gives us 7 factorial divided by 1 factorial. So I'm going from 7 all the way down until I get to 1, and I'm going to cancel out the 1, which is all we did. We canceled out the 1 as a portion of it. Okay. If you have a permutation of 10 things taken 0 at a time, we would have 10 factorial over 10 minus 0 factorial, which is going to give us 1. There is only one way to take 0 things, and that's by taking none of them. That also leads us to a special rule that says 0 factorial is equal to 1. There is only one way to take 0 things, and that's by taking none of them. Okay. When we have a permutation that has duplicates within it, maybe not all of the things are duplicates, but maybe a portion of it is duplicate, like the word Ohio, and we want to take 4 letters and we want to arrange them in 4 different spaces. However, if I write O-I-H-O using these O's, and I also arrange it O-I-H-O using O's there, these look exactly the same. They are not distinguishable. So the way that we take out our duplicates is we're going to divide out the duplicates. Right? So we take our regular permutation formula, because our bottom part got rid of the spaces that we didn't want. Now we need to get rid of the duplicates. And so when we have multiplication, the way that we get rid of things is to divide out. We're going to divide out by anything that is a duplicate and how many of the duplicates they are. So in Ohio, let's look at our different options. We have an O, an H, an I, and an O. So for each section, we would say for the O's, I have 2 of them, and we use the factorial because there's different ways that we can then count the order these letters. For the H, I only have 1 of them, and for the I also only had 1 of them. We don't have to write the 1 factorials, but I want to show you that what we're actually doing is counting each of the different individual events. So these are duplicate events. So we have an event of an O, an event of an H, and an event of an I. And we have 2 of the O's, 1 of the H, 1 of the I. So we are dividing out by any duplicates. It's important whenever we are talking about distinguishable events, as you have in 47 through 54, that we first have the total amount. So we have the total events that could happen, and we are going to divide out any duplicates. Right? So for an example, we have the word Missouri. How many different events do we have? We have an M, I, S. There's 2 S's, O, U, and R, and then there's actually 2 I's. So within the I's, we have a duplicate, and within the S's, we have a duplicate. So we'd have 1, 2, 3, 4, 5, 6, 7, 8. We initially have 8 letter tiles. Think if you're doing Scrabble, a permutation of 8 letters, taken 8 at a time. We want to use all of our letter tiles, but how many are separate? We have 8 factorial. This is our first one. 8 minus 8 is 0, so we have that 0 factorial, which really gives us a 1. So our total number of ways that we could order, lots of different orders, would be 8 factorial. However, we've got duplicates because I could have I in different places, but I can double them. So I have 2 sets of I's I need to take out, and I have, a duplicate of S's that I also need to take out. Now, 2 factorial times 2 factorial is not the same as 4 factorial. It is 2 times 1 times 2 times 1, which in this case is 4, but it's not the same as 4 factorial because 4 factorial is 4 times 3 times 2 times 1. So make sure that when we have factorials, we are not multiplying and combining those into a separate number factorial. These are indeed two separate events. They need to stay separate, and you can see that whenever you multiply them out. Okay, let me see if there's anything else on homework. For 62, if you were looking at different ways that we were going to display things, these are separate events. So we would write out our counting like we would for our fundamental counting, and it says we've got keyboards, we have trumpets, and we have guitars, right? Would be in the spaces that we have. We have 3 keyboards, we have 2 trumpets, and 2 guitars, but it says each of these are identical. So that means there's no way of telling which keyboard is first. They're not colored. They're not a different style. So we're going to have duplicates. So that means we have a duplicate for keyboards of 3 factorial, a duplicate of trumpets of 2 factorial, and a duplicate of guitars of 2 factorial. So the number of ways that we can take 3, 4, 5, 6, 7 things here, right? Taken 3 at a time that we're looking at, we would take out our duplicates. We could also say 3 times 2 times 2 gives us 12 different items, and we're going to take out duplicates from that, right?